The floor is yours, Heinz. So, welcome.
Thank you so much. And it's a real pleasure to be back in Athens. It's actually my first conference talk, like live conference talk, since I think October 2019. And the last time I started my conference talk by saying, this is the last time I'm going to speak at a conference for a while. I didn't expect it to be this long. But we're going to talk about Project Loom today. And if you love my newsletter, do subscribe. You'll find it interesting. And come say hello if you want. After the talk, during the conference, I'll be around. Also, tomorrow I'm doing a workshop on reflection. So if you're interested in some a bit more meaty Java topics, there'll be a nice, fun time. It's a deep dive, actually, not a workshop, they call it. All right, so Project Loom, I've been talking about this for years and years and years, and it's actually coming now. So for Java 21, the plan is to release Project Loom. And not all parts are ready. There are some parts which are still in incubation mode. They've got a couple of things there, structured concurrency, scoped variables, but most of it is getting ready. And we can use it today for doing some pretty cool things. The additional modules have to be added with add modules, JDK incubator, concurrent, but the other parts are going to be part of Java 21. It's been part of Java 19 and 20 preview, the virtual threads, but now they are actually coming. So this is really very exciting. And everybody seems to be talking about virtual threads nowadays. So they're just a quick motivator why we need them. We need them because, well, asynchronous code is difficult to debug. You don't have a normal stack trace like you have with a traditional code. And so it's more difficult to debug to step through the code like that. And on the other hand, it also doesn't really scale to be able to have a one-to-one mapping between Java threads and native threads, platform threads. So I was doing some work for a company once, and they had written a system where every time a customer connected, they would spin up 5 threads. And after about 1,000 customers connecting, it crashed. And yeah, it didn't work. It would work with virtual threads, but it didn't work with platform threads. Just after a certain time, you run out of memory and run out of native threads, and boom, you're dead. So this is why Project Loom was started. The idea is that you can have a lot of virtual threads in a virtual machine. It's like the example is you can have virtual memory, where your virtual memory is far more than the actual memory that your machine can support. And they've supported this throughout the virtual machine with networking supports it, Java concurrent supports it. Not everywhere, but in most places where you'll find blocking happening, you have a support, but not everywhere. And this is important for us to get ready for what this can give us. Now, just in terms of thinking, there are 2 main ways in which we use threads. The one way is in parallel computing, where you're breaking a big problem into smaller problems, and then you're solving them individually, and then merging the results together again. This is not what Loom is for, okay? In fact, Loom will be really quite bad at doing this. For doing parallel computing, you want to use fork join, you want to use parallel streams, but you don't want to use virtual threads for parallel computing. It's not made for that, and you can get yourself into trouble by pinning your threads. But where it is useful is for concurrent computing. And the idea is that you still break up your work into different chunks, but where you are waiting for something, you're doing something else in the meantime. Ted had a great talk just now, and my mind had just drifted to something else, and he called out my name. So I was like, whoop, got to keep focused, got to keep focused. And that's how we are. We're always trying to do other things at the same time whilst we're waiting for something to happen. Whilst you're waiting for the airplane, you're doing something else as well. You're not just going to sit there. Maybe you'll talk to somebody, or you'll write an email or something. But there's always something that you're doing when you're waiting for something. You don't just sit there. Even if you're just thinking, that's still doing something. And that's the idea with concurrent computing, is that we don't just sit looking blankly into the sky. In the meantime, we spin up more threads to do the work. And this is where virtual threads can really help us, because they make it very, very easy to just create millions of tasks which run independently. All right, so I'm going to show you a quick example just to go through the thinking process of how you'd solve a certain problem. This is a sort of a web search. We're looking for the best deal, and I'm going to, first of all, scan the requests for search terms. Then I'm going to search partner websites. And of course, each time I'm sending a request to a partner website, I'm going to have to wait for them to answer. And then I'm going to also, of course, have some advertising links. You have to make some money. And then I'm going to collate the results from the partner website, bring them back together, and then show the result. Now, that's the idea. And some of these steps you can reorder without affecting the result. For example, you can, at the same time, create the advertising links as you are searching the partner websites. But you can't show the results until you've done everything. So if you did this in a single-threaded way, it would be very simple. You'd simply say, well, I'm going to scan for search terms. That's going to give me the list of search terms, and I'm going to search on partner websites and produce a list of the search results. And that might take some time because I'm sending out all these links, all these requests, all the search to all the partner sites. Then I'm going to create advertising links, and lastly, I'm going to collate the results and show the final product, show the final page. So that's the sort of the four-step process to get the page. And what I did was I gave an artificial time budget to each step. So if you did it one at a time, it would take 4.3 seconds. That's not real 4.3 seconds. It's just a time budget for each step, and that's what we get to. Now, if we did this the older way, the old traditional way with callables and futures, then what we could do is we could start the search in the background, and we might actually get better performance that way. And if we're lucky, by the time by the time we finish doing the advertising links, maybe the search results already are there. So here's what the code would look like. It's a little bit more involved. I've got an executor service, and inside the render page, you can see that I'm scanning for search terms same as before, and then all I've done is I've wrapped the searching in this callable. So that's happening independently with another task. However, the callable, what I'm doing is I'm searching all the partners, but still sequentially. So there's still a sequential search happening over there. And then I submit that, and at the same time I'm doing the create advertising results, links over here, and then I collate the results. But collate results has to wait for all the results to be done before I see it. So it doesn't really win us that much. There's a lot more involved, but we go from 4.3 to 4.1 seconds, because all you're doing is you're parallelizing the advertising links, which doesn't take that long. So if you want to, you can go and do completable futures of this. Now, completable futures, I've really thought about, I've tried to come up with a good example of what it is. To me, it's a way of manually constructing an abstract syntax tree of your concurrency logic, right? That's what you're really doing with completable futures. And it's really easy to make mistakes with it. For example, to return from a method without having finished the work, and then it sort of works in certain circumstances, but not always. So if you want to sort of fork work and join it back together again, it's really quite difficult to get that right with completable future. I'm going to do this with spawning a bunch of tasks, forking them, and then joining them back together again. And the code is going to be a bit faster, but it's going to be a lot more complicated. Also, with completable future, you actually have to know what pool it's going to be running in, right? Because you have to know whether it's a CPU-bound task or an IO-bound task, because you don't want to run it just in the default pool. The default pool is either going to be the common fork join pool, which is great for parallel work, but not great for blocking work, or it's going to be a new native thread for every single task, okay? There are situations where that will happen, where it will make a new thread every single time you submit you try and do an asynchronous completable future. So you have to be a little bit careful. It's best to hard code what the pools are supposed to be. So what I did was I did activity diagram, just to remember, just to show what we're trying to do, we're going to fork into the advertising links and the scan for search terms. Then we want to search all the partner sites concurrently. We don't want to wait for them all to be done one at a time. We want to launch all the searches and then collate them all together and join, and then we're done. So the way that this would look is fairly complex. I'm not going to go into all the details. Basically, I'm going to have a method that each method is going to create another completable future, and then we're going to join them all back together again. So I'm just going to go over this just to show you there are lots and lots of methods for each different element, and then once you're done, you can collate the results, and you're done. So I'm not going to explain it. If you're looking at the recording, you can stop it and, and puzzle it out. But it's a lot of mental process to get that right, and there's no really easy way to link the activity diagram to the code. So it's always a problem. If you have a nice diagram, it's easy for that nice diagram to go out of sync with your code, and then you have to always try and figure out what's actually going on. So could we do this with plain threads? The answer is we could, but it just wouldn't scale very well. And the code would be a lot simpler than with a completable future. And here's what it would look like. Basically, what I would do is I would make a new thread for the advertising links right off the bat. And I would simply say new thread, pass in a runnable. The runnable creates the advertising links. Then I'd start that thread. Then I would make a collection of threads. Each of these threads is doing a search on partner sites and then collating the results. So it's, again, really, really simple. It maps much more closely to the original code. And then we join with the advertising link to make sure that that's complete before we finish. And we also join with the search and collate threads, all of those, to make sure they're all done before we exit from the method. So this works very well, but it starts, in this case, I've got 10 partner sites. So it's going to start 11 threads in order to do all the searches. And that, of course, is not something that we can do. Generally, we can't just make an infinite number of platform threads because we're going to run out of memory. But you can see it does complete more concurrently and in faster times, 0.5 seconds. So this is not ideal either. Platform threads are not the way to go. And it's not scalable. As I said, even if you have one platform thread per client, it's going to bring your server down. And here we're going to potentially start dozens of threads, depending on how many partner websites we have. And this is where the virtual thread comes in. Basically, the virtual thread is very lightweight. You're looking at typically less than a kilobyte per thread. They're very fast to create. And I mean, I just tried it out. I could fit 23 million virtual threads into 16 gigabytes of memory. So they're abundant. You don't really have to worry too much about how many you're making. And in fact, you don't even have to worry about pooling them because they're so cheap to create, you just make them and throw them away afterwards. And the way that they're executed is they are executed by normal platform threads. We call them carrier threads. These carrier threads come from a fork join pool at the moment, and I think it probably will stay like that for a while. These carrier threads are always daemon threads. You can't, it's not really an option to not have them daemon threads. And so the virtual threads will simply disappear if you don't have any non-daemon threads left. So just be aware of that. Now, you can configure this pool to some extent, the carrier thread pool. You can specify what the desired parallelism is. So typically, this is going to be the number of hardware threads in your system. So on my MacBook Pro, I've got 8 cores, and I've got hyper-threading. So it's going to be 16 threads, and 16 is the desired parallelism of this virtual thread scheduler. But this can actually increase temporarily if you hit certain types of managed blocks. So for example, if you're doing a wait, a synchronized wait, then this scheduler, the virtual thread scheduler, might actually increase the number of threads in your system. Usually it's going to be like 4 times or 10 times or 16 times. the number of the desired parallelism. So whilst you blocked, it just spins up another platform thread. And this you can configure with max pool size. So it's just minus D JDK virtual thread scheduler parallelism and max pool size. That's how you can configure how many threads you're going to make up to. And the idea is that if you block, then it's going to, if you block with for example, the modern synchronizers, the reentrant Lex lock and so on, then it's actually going to move the carrier threads, the virtual thread off the carrier thread and make that available for somebody else. So, and this also works with the synchronizers you have in Java concurrent. And in most places in Java nowadays, virtual threads just work. You don't have to do anything special. And you don't have to worry about the number of, you don't have to worry about managed blockers in most cases because they've implemented this right inside the abstract queued synchronizer. Oh, I've got a little gift for you. It's not Sikudia, I'm afraid. I live on the island of Crete where, you basically, if you don't have Sikudia at 10 in the morning, then there's something wrong with you. But it's a little gift, but it's a coupon which expires at 12:45. So we've still got a bit of time to get that. So tinyurl.com/devox-el. All right. So if threads are unlimited and free, why don't we just make virtual threads for every task? If you look at the original code, looked like this, and here's how we can do it with virtual threads. So they've got some new methods. Instead of saying new thread and then starting the thread, we can just say thread.start virtual thread, and you're passing the runnable in there. The whole code is actually a lot simpler than before. We simply are starting new threads with abandon. We don't care how many we make. As I said, you can make millions of these things without running into any trouble. And then we join the threads just like we did before. And so if you switch from normal threads to virtual threads like this, the system works without too much extra effort. And again, it's about the same speed for this particular code. But if you had a lot of threads being made, then the virtual threads would beat the platform threads in most cases. So there are a couple of ways you can make these threads, either with thread.start virtual thread. This has been with us since Java 19, but Java 21 is now it's now part of proper Java 21, not with preview features. Or you can say thread.offVirtual, which gives you a builder to construct the thread, and then you can say .start on the runnable. And there's also another ways we can make executor services that use virtual threads, and the one is executors.new virtual thread per task executor. And it's not a thread pool because it never keeps track of what threads it's made. It just makes them, and once you're done, they just die. It never reuses them, and they just get thrown away afterwards. And what's also nice is what they've added to Java is that the executor services are now auto-closable, which means that they first of all, if you exit from there, if you try and close it inside the try with resource, then what happens is that it's going to call shutdown. And there's one little thing that I don't know if anybody knows this, but if the thread gets interrupted whilst waiting for the shutdown, if it gets interrupted whilst waiting for await termination, it then does a shutdown now. So you can cause a shutdown now to happen on your thread pool. All right. So here's what it looks like with the thread pool. So I've made first of all the main pool. This is now and I've wrapped inside a try with resource block. And you see main pool.submit, passing in the runnable. And then I'm making another submit, and this time I'm doing the scan for search terms, and then I'm making a second pool. Now the reason I need the second pool is that the moment that I get past the second submit, it's going to try and close the executor service main pool, and it's going to, therefore, you won't be able to submit new jobs to it. So if you need to do nesting of executor services like this, or of tasks, you'd actually need to create different pools. But it's very cheap to make these pools, so it really isn't a problem to just make another one. All right, so this works nicely, but it still is a bit unstructured. It's not really the right way of doing things. And that's why we've got this new idea of structured concurrency. And this is a better approach. It's not done yet. This is in the incubator stage of Java. But the idea is that you'll be able to write code like this in a more structured way. So for example, I'm going to say var scope equals new structured task scope dot shutdown on failure. There are two main ones, shutdown on failure and shutdown on success. And if any one of those forks fails, then the whole thing fails. All right, and then you can see, I simply say fork, and I do another fork, and this time I don't have to make a separate scope. I can, but it doesn't really help me in this case. And so what I do is, once I've forked everything I needed to do, then I just join the scope, and that will wait for everything to be done, or if one of them fails, then the other one get failed as well. Now, there are some advantages with this approach. The one advantage is that there's a relationship between all the forked tasks and the thread which is calling join. If any one of them fails, if the main thread fails, it gets interrupted exception, for example, or if any one of the forks throws an exception, then the whole lot is cancelled. And I'll talk about cancellation a bit. And then afterwards I say scope.throw failed. So if any one of the tasks cause an exception, that will then throw an execution exception that wraps the original exception. All right. So, waiting for time, 41 minutes, okay. So the one thing that we should consider is that if I've got a method that runs a little bit longer, and by that I mean if it does a little bit more work. Now ideally you shouldn't do a lot of work inside your virtual threads, because whilst you're doing CPU intensive work, no one else can use that carrier thread. You've basically claimed that and it's yours now. But if you are, you need to check whether or not you've been interrupted. And even if you're not doing that, if you catch interrupted exception, ideally you need to propagate that status, or at least throw a cancellation exception. So we don't want to just swallow interrupted exception. This is something we need to check your code base, because there's a lot of code out there where people simply catch interrupted exception and ignore it, don't do anything with it. So I've got a little demo I want to show you. Let's see if this microphone takes over. Is it going to work? So all right, so let's put this up, make this bigger. Okay. So this is using Java 21. Oh, that's the wrong project. Let's try the right project. There. Okay. So let's make this the structure demo. Okay, so what we're going to do, we want to run this demo for 3.5 seconds, right? And so what I'm going to do is I'm going to make a timer that's going to interrupt the current timer, the current thread after 3.5 seconds. So let's make a timer over here equals executors dot new single scheduled executor. Now, what's pretty cool is what you can do with virtual threads. Normally, when you've got timers, you're basically using up more and more platform threads for your timers. But what you can do here is you can simply say thread.ofVirtual.factory. So you're going to make virtual threads for your timers. And so you're going to have a single thread that manages all of your timers this way in your whole system. So as opposed to having each of you've got a timer, you've got another thread that manages that. And then we're going to say timer.schedule, and now we need to know what the current thread is. So thread current equals thread.current thread, that's my current thread, and I'm going to say schedule to say current, interrupt, so it interrupts the current thread after 300 milliseconds like that, okay? So this is this is the time that's going to interrupt the current thread after 3.5 seconds. All right, now we're going to make this structured task SOAP. So we're going to say try var scope equals new structured task scope.shutdown on failure. That's the one I want to do this one. And then we're going to have 3 forks. The first fork is going to be, has an infinite loop that swallows interrupts. Okay? So we're going to do this while true. Try thread.sleep for 1 second. And we just type here fork 1, print out fork 1, sleep 1 second. And when we say catch interrupted exception, we just ignore it. In fact, we can say ignoring interrupted exception. Okay? So that's the first fork. It's an infinite loop that simply ignores interrupted exception. And then the second fork is going to be almost exactly the same, except that it's going to not ignore the interrupted exception. So we're going to just propagate. Now, in the past, most of the time when you submitted something to a pool, it was a runnable or a callable. Now it's only a callable, which is great because we can simply throw an exception here. So I'll do those two first. And then we're going to say scope.join to make sure they're all done. And it's waiting for them to finish. Of course, they won't finish because it's infinite loops. And then I'm going to say scope.throw if failed. All right. And throw if failed is going to throw the execution exception. This one over here, execution exception. All right, let's run that code and see what happens. So what you'll find is that it's going to print fork 1, fork 2, and then after it's interrupted them, fork 1 just continues. So, and this is my point, is that you should be very careful with interrupted exceptions in your code to not just ignore them going forward, because it's going to affect the way that your structured concurrency will work. The only way to propagate the information that you need is via interruptions, to shut it down. You can't stop a virtual thread. So the only chance you've got is through interruptions. And if you turn it off, you can't solve that problem anymore. So if you make a third one here, this is now fork 3, this is going to be a bit different. We're going to say long up to equals system.current time millis plus 1,000, while system.current time millis is less than up to just spin, and then we're going to print fork 3 again. So here, I don't care about interruptions. I'm just running and not caring. Now, this is really bad code for many reasons, of course, but you'll notice it also doesn't react at all to the interruption. So the fork 3 will just continue as well. So that's not great either. So if you need to do something where we have to do some calculation that might take a little bit of time, it's a good idea to make it cancelable so that you can say, for example, thread.currentThread.is interrupted is false. You can put that over here, and you can even do it inside the while loop whilst this and not interrupted. And this means you can break out, so you need to say return null, just to make sure that we actually have some value coming back. And now you'll see it's also going to be able to cancel. It can also cancel. So if you fork 3 is also cancelled. Now, of course, you can also do instead of interrupting the thread, you can also say join until some deadline as well. So this is really the way we're going to go with structured coding. The idea I mentioned earlier in this managed blocker, where it will temporarily increase the number of threads, is something that was really important when we use native threads. We wanted to limit it within the fork join pool. And it started with Java 7 with a phaser, and they've been adding more and more classes that use a managed blocker. But the managed blocker only really helps if you are blocking, right? If you're doing just number crunching, it doesn't help you at all, or very little. The one place where they still use it is with synchronization. Or any time if you need to synchronize and then you're blocking something. So synchronizing is okay as long as you don't synchronize whilst blocking, or block while synchronizing. So if you're synchronizing in order to protect memory, that's absolutely fine. All right, they've also re-implemented all the socket APIs. That's something you shouldn't notice. It's just done. But there are a bunch of things that they've also done which are interesting. For example, the future now has result now, exception now, and state. These methods which you can use in order to manage the results using a stream. I've got a demo called timeout and pull. I'll just show it to you quickly. It'll just take a second. And I'm not going to code anything. I'm just going to show it to you. Here I've got a randomizer that generates random numbers between 0 and 10. If the random is less than 7, I return a value. If it's less than 9, I throw an exception. Otherwise, I sleep for 10 seconds. And then what I do with this is I iterate over that and I check, and I also interrupt the thread as well, I think. Do I? Yeah. No, I don't. Okay. So what I also do is I can then stream the randomizers and I can filter, for example, is the state failed? Was there an exception? And then you can look at all of these values. So this is quite a nice little mechanism where you can find out, for example, how many illegal state exceptions did we have and so on. And that's the purpose of these additional methods. So if you see them, that's their purpose. Also, Java networking is now interruptible with virtual threads. So if you're, for example, waiting on a socket, you can interrupt the thread which is waiting, which is something new. They've rewritten reflection to avoid native code. So it's not all it's all based on method handles. Also, if you make a thread dump, in the past the thread dump was maybe a couple of thousand threads. Now it could be millions of threads. So you can dump it to a file, a JSON file format, for example, and it doesn't pause the application anymore like it used to in the past. The actual stack depth is the same as virtual machine native threads, so that doesn't change. The other thing which is interesting is that with normal threads, your virtual threads were GC roots. So when they did a GC, they'd look at your normal threads, and whatever they used was considered as the root of your memory. But since virtual threads, it doesn't work like that anymore. Or virtual threads aren't like that. They aren't GC roots. So if nobody has a handle to virtual threads, then they can be garbage collected. And that's caused some interesting demos. Also, it says at the bottom here, virtual threads that cannot be unblocked are garbage collected as well. So, for example, if you, for example, create 1 billion virtual threads, and the last thing off your thread is something which can't be unblocked. Like, for example, you're simply saying lock support.park without having a way to unpark it, then they'll just be garbage collected. And I've seen demos where people demonstrate how amazingly virtual threads work, and they're just constructing millions and millions of these things, but they're just being garbage collected as soon as they're being made, because they're no longer reachable. They've actually removed the ability to do thread.stop, and that is true for virtual threads and for platform threads. Since Java 20, you can't anymore stop a thread, which I think is great. A virtual thread has a reference to a thread group, but thread groups don't have a reference back to the virtual threads. So that's also a little thing to know. All right. The thing that you need to know is that synchronize is not fully compatible with Loom. So if you run this code here, with this code, you'll find that I'm creating 10,000 virtual threads. they are synchronizing on a monitor and saying monitor.wait, and the wait is the problem, not the synchronize, the wait is the problem at the moment. It will create additional threads through the managed blocker, but there is a limit, and it's going to eventually run out of those threads, and so you won't see any output. You'll never see this done at the moment, but they might fix this in the future. So if you've got code that works with wait notify, you need to change it to reentrant lock or use high-level constructs. So they do use blockers. This is what the code looks like, blocker.begin. So they use managed blockers, but it still isn't fully compatible. So we might have to change our code for this. Unfortunately, the idioms are more complicated for reentrant lock than for synchronized. Luckily, you can debug this. You can actually trace the pinned threads. If you say minus d jdk.trace pinned threads equals full or short, it will show you all the places where you've got code which is blocked whilst being synchronized. So that's great. Also, they've turned off bias locking. Bias locking helped in the past when we had older hardware, but nowadays it won't make a difference with modern hardware. It's very unlikely you'd spot the difference. If you try an older version of Java, you can try put it on again and see if it makes a difference, but I'm very doubtful it will. And the reason is I wanted to move faster with Java, being able to change it, and bias locking was a really interesting hack that supported a particular use case, which is not very common. They were flip-flopping about thread local. They did have the idea to turn it off for virtual threads, but there's too much code which depends on thread local. And so thread locals are now supported all the time for virtual threads, but it's best not to use them. And especially not for caching expensive resources. That's the wrong place for using thread local and virtual threads, because virtual threads are not reused. You make them once, you throw them away. They do make sense. They do make sense if you want to store some state within a context for some networking operation, but it doesn't make sense for any expensive objects anymore. Also, virtual threads don't have a name. Is that 10 minutes left? 3 minutes left, okay, because I couldn't see the writing. All right, 3 minutes left. So virtual threads don't have a name. They are unnamed, but you can generate a name from the thread ID, which is unique. The states are different. This is the original states. This whole state machine is a lot more complex. I drew this diagram in 2020. I spent a couple of days figuring it out. And I haven't looked at it since, so it might have changed. The point is, it's a lot more complicated. And you have and these states map in some cases to the thread state, other cases they don't. All right. Also, the one thing which is a bit of a pity is that the I/O streams actually use a lot of memory. And I noticed this. I did a demo a long time ago where I had 2 million sockets open, sending to 2 million sockets on the other side, and each had 2 million virtual threads. But the problem is that if you use something like an input stream, then they use too much memory and you can't really scale it. So you'll have to use different techniques for that. So just look at how the print stream looks. It's like 17.4 kilobytes to make a single print stream, right? A buffered reader is 16.5 kilobytes, right? My first computer was like 48 kilobytes, so you don't really, and this doesn't scale very well because it's way more expensive than your virtual threads. It used to be a bit worse. They used to use a bit more for the print stream, so they have reduced the size, but it still is too much. Also, deadlocks are very hard to find with virtual threads. I've got a newsletter 302, look up on a website, search for that, you'll see how to do it, but it's really quite difficult. If you've got a deadlock between a virtual thread and a normal thread, you might be able to find it. If it's between two, if it's with reentrant lock deadlocks, you won't find them. They're just like impossible to find. So that's really challenging. You can find it with -d JDK stack track all threads equals true, and then if you dump with J command to a file, you might be able to see where deadlock is. But this actually is a problem that hasn't been solved well. Especially with reentrant lock, it doesn't pin the carrier thread, so there's no way to know that you've got a deadlock. All right. As I mentioned already, Loom is not for parallel programming, it's for concurrent programming, so we don't want to do a lot of CPU work with it. I'm going to skip this part here. Okay. So if you already have asynchronous code, I recommend leaving it, don't touch it. Unless you need to add a lot of new features. Retrofitting something to what is already there probably won't help you that much. But if you're starting with new projects, it might be something to look at. The one thing which is not quite good yet is back pressure. They recommend you use something like a semaphore, but the semaphore isn't really the best way of working. It's not a very sophisticated construct, so be careful of that. Just don't forget this, and I've got one more thing I need to tell you, and that is, as I mentioned, 21, it's ready, but some parts are part of the incubation stage. So, that's it from me. If you have any questions, we probably don't have time for questions, but you can come to me and ask me afterwards.
Heinz, thank you so much.
Thank you.